All right, let's talk about molecular nomenclature. We're not going to do super complicated nomenclature in this course, but so we're going to keep our focus on binary stuff, and we'll get into this in a sec. We're binary. We can have two different elements there. In the case of ionic compounds, right? Ionic names are based on the charge, right? But we can't do that with molecular compounds because there's not a charge involved. Okay, but the name convention feels similar, right? You're going to have a first name and a last name. The first name is a cation-like name. This last name is an anion-like name, and I'm going to show us how to figure this stuff out. All right, so when we're thinking about things are in my way. Okay, binary stuff. We're thinking about two different elements. Okay, our easiest scenario is going to be if there are only two atoms involved. Okay, there's not a lot of these, but the rules are going to follow the same way. The first element gets the element name, and the second element gets the anion name, which is the IDE ending that we've talked about before. So here, if we have HCl, H is hydrogen, so this is hydrogen, and Cl is chlorine, so this is chloride. Great. Si is silicon, so this will be silicon carbide. Okay. There's not a lot of these, and we'll I kind of get I don't know if we'll know why, but we'll see some other stuff that is a little bit more universal. If you have more than two atoms, it still counts as binary as long as you only have two elements there. But because we don't have charges to worry about, we're going to have some way to get those numbers into the name so we know what we're talking about. And for that, we're going to use Greek prefixes. You probably know some of these from previous studies of whatnot. But they're here: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Okay, the previous rule still applies. So we're going to have the first element is the element name. The second element gets the anion name with the IDE ending. And then we're going to throw prefixes in there in the front of each element to say how many are there. Okay, there's two big comments we have to make here. You don't put mono on the first element because then 90% of stuff would start with mono, and that's just too much. And if you have oxide as your second element, your prefix, if it ends with an O or an A, you're going to drop the O or the A. And that's just so we don't get a mouthful of vowels. And we'll see that as we do some examples here. Okay, so one nitrogen, two oxygen. So this is nitrogen dioxide. Right, iodine and three bromines. So this is iodine tribromide. We have silicon in front. And then we have four chlorines. So this is tetrachloride. Okay. Here we have two nitrogens and an oxygen. So we need a prefix in the front. So this is dinitrogen oxide. Okay. Actually, we should say dinitrogen monoxide because there's one oxygen there. Okay. And so we drop that O on mono because we have oxide. Okay. Here's another handful of examples. If we've got CO2, we saw these in the other video, carbon dioxide. This is carbon monoxide. Iodine, three fluorines would be trifluoride. Remember, fluoride is UO. Here we have IF. So this is iodine monofluoride. Okay. Cool. Not too terrible. And as we always say, if you can do it forwards, you can do it backwards. then writing the formula from the name is relatively straightforward because the name is the formula in terms of words. So dichlorine pentoxide means we have 2 chlorines and 5 oxygens. So Cl2O5. Oxygen difluoride would be 1 oxygen and 2 fluorides. So that's OF2. And then bromine trichloride, that's 1 bromine and 3 chlorines. So that's BrCl3. Okay. Hopefully that makes sense. If you have questions, obviously let me know, right? This isn't too terrible. The big thing we have to remember though is don't start throwing prefixes into ionic names. It's very easy to fall into that trap, so we don't want to do that. Hydrogen has some weird things going on with it, just because a lot of these names for things that have hydrogen in them came before the rules for naming stuff did. So we have a lot of common names here. This is a handful of common names of hydrogen compounds. I want us to know 3 of these. Right. The other ones, actually, we'll talk about these when you get into organic, but we don't have to know these for right now. Ammonia, water, and hydrogen sulfide. If you were to come up with a name, hydrogen sulfide is just dumb because it should be dihydrogen sulfide, but that's the IUPAC name. Hydrogen sulfide is the common name. Weird. Okay. Excuse me. But it's important to know, like with these common names, if you're looking up information, you want to always use the common name when you do that, right? If you go and you want to look up information about water, you better look under W, because if you look under dihydrogen monoxide, you're not going to find anything there. Okay. While we're thinking about it, I'm going to go ahead and tell you that our secret word for this is otter. Otters. Okay. I don't know why I said that. Okay. Anyway, so there's that. Yeah. Other things that have hydrogen in them that are molecules also act as acids. And so we're going to talk a lot about acids in this course too later on. Right now, I'm zoning in on naming stuff. Okay. We can tell we're dealing with something that can act as an acid because the hydrogen is written first in the formula, right? And our good general definition for acids are going to be anything that produces an H plus ion when dissolved in water. Okay. Here we're looking at binary acids. There's not a ton of these. The naming is kind of similar to what we've seen before. Um, the 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 twist is that depending on what the situation is, you could name it as a molecule or you could name it as an acid. So, for example, we saw hydrogen chloride before, HCl. Okay. If it's acting as a molecule, we'll call it hydrogen chloride. If it's acting as an acid, then we're going to call it hydrochloric acid. So a lot of these, you might see this AQ here. This means aqueous, which means dissolved in water. And so when it's dissolved in water, it's going to act as an acid. So if it says aqueous, then you're going to use the acid name for it, or you'll be told which way to do it. Eventually, we'll get into the habit of knowing what's going on. But so the way this is going to work is your binary acid contains only 2 elements. One of them has to be hydrogen and the other one is something else. And whenever we name these, we're going to say it's hydro something ic acid. Okay, so hydrochloric acid is HCl, or hydrobromic acid, HBr, hydroiodic acid, HI, all this fun stuff. Excuse me. It's also important, I want to point out here that HCN counts as a binary acid. Okay, and as we'll see in a bit, CN minus is called cyanide. And so HCN is hydrocyanic acid. Notice in our pattern here, all of these are halogens, FCl, halogens as you go down the group. CN is known as a pseudo halogen. It means like a lot of the chemistry of cyanide behaves similarly to those of the halogens. Okay, so that's why this counts as a binary acid. Okay. Yep, that's it for this one. Let me know if you need anything, and I will be here for you.